Okay, I've got a rather enormous title here, rather grandiose of my paper, and I'm only doing an aspect of the paper today. There'll be a second and a third follow-up meetings to do the same. Today I'm going to discuss electromagnetic soliton theory. Now, the first thing that I will just show you is a thought experiment that actually set the thought process through. If I look at this particle accelerator and deaccelerator that you see sketched in front of you, the electrons accelerate between, what's going on here? Mouse, okay. Can you see my mouse?
Yes, yes.
Good. The particles accelerate between A and B, and in doing so, power is delivered by the battery marked V1 here. Between B and C, they are at equal potential, so there is no acceleration or deceleration. And then from C to D, I deaccelerate the electron. So when it comes out at the end of the apparatus, it's got the same kinetic energy that it started off with here. And because I can keep this flow of electrons on indefinitely, I asked the question, how is this current I1 and I2 maintained? The physics theories tell me that current is a flow of electrons, but the question is, where do the electrons originate from and disappear to if this particle beam is kept on for a long time? So I propose to separate the electrostatic from the electromotive domains in electromagnetic theory. Before doing, why is this not working? I must just click here. Okay. Before doing so, I'm going to show you a quick video at the moment. What is interesting, I'll show you two photographs. The left is taken from out of space, and the right was taken in a photograph. And the explanation for the for what NASA says for the WR140 that unfortunately didn't put it in there, is that this is dust spirals that is being blown off a binary star. But let's just watch this a little video now. So it is quite interesting, and I must just get it up. No, it's not that one. Where did I put it? Here we are. So let's just start this. I saw this for the first time.
Everything is plugged in. Step one is to create a basic plasma glow discharge that can be measured. When we fire up the chamber for the first time, we really have no idea what is going to happen.
Water's going down, that's good. Water's going down. Our helium is coming up, which is 4. We're getting a lot of hydrocarbons in there.
We adjust pressure, voltage,
so I'm going to introduce a little more helium right now.
Current,
a little bit more,
and time.
And then we'll take another sample.
Time is also a key element.
You want to shut it
when
off,
the proper combination of these factors is arrived at, the plasma spontaneously ignites.
There we go. 0.4 is going down. Let's shut it off. Pumps and argon is off.
A glow discharge forms in the chamber.
So we just leave it here. It'll start climbing by itself.
Yes.
Look at the emissions coming out. Look how bright it becomes.
We adjust the various parameters to obtain a variety of plasma regimes.
Look on the surface. See the glows?
What we're observing has no clear precedent. We are seeing things we did not expect.
Look at the pressure changes. Nice, nice. Look at the spin. Look at the spin. Yeah, look at the spin. What we're starting to see right now is a new sphere starting to form around the anode. And it's
after many run-throughs, we were able to define a number of consistently reproducible phenomena. This is the anode glow discharge. The plasma glow discharge, coronal discharge region,
Here we're at 3-4.
and the low density ionization region.
We have argon pressure. We're not doing slow. Yeah, open up the argon.
At one stage, a uniform plasma sheath forms around the anode. Then tufts of high-energy plasma discharge appear just off the surface of the anode. As we vary parameters, the plasma discharge changes. The tufts move, then start to spin around the anode. Spicules and hair-like discharges form in the transition region.
Even though we have the voltage set at 600,
A high concentration of ions collect just off the surface of the anode. As the concentration of ions intensifies, it reaches a critical density, then explodes out into the chamber. At no time do we see an arcing between the anode and the cathode during the discharge. To our surprise, we find that the cathode is not playing as much of a role as we thought it would.
very intense low load. 2.5 amps. Yeah. 10 volts. Okay, it's starting to grow here, and here comes, look, here it goes.
We think we are seeing a new phenomenon. We are calling it intense plasma flow discharge. Plasma double layers.
This is happening at 3 torr. We've never seen anything like this.
Here, we are looking through numerous rotating translucent plasma spheres. These intense plasma flow discharges come just before another phenomenon appears. Then we see intense plasma tufts in stable double-layer spherical striations. Notice the color and intensity differences of each plasma sphere. As the striations form and stabilize, the anode cools down.
Okay, now that was in 2014. I will show later another video from this group when they developed their technology of this. But before going there, that was one of my inspirational videos that I had or seen. You know, I actually know these guys. I've met them at conferences a number of times. But anyway, let's just think what a wave is. A wave is basically defined by the D'Alembert wave equations, which we know here. A pendulum is not a wave, you know, even if it's Lorentz boosted. And this is basically a snide against the people who do topological solitons. They all use this sort of formula, and then they say this can move if one Lorentz boosted. But anyway, now let's just think of three vectors. We all know the relationship of the unit vectors that define the axes in terms of the cross product of the axes to define a right-handed space. Now, in this right-handed space, we put in three vectors: a velocity vector ut, an activator vector at, and a reactivation vector rt, and apply exactly these, you know, are basically defined by this. Now, the problem is, if you know, this shouldn't be a Z here, this should be a R1 here. If you now think of a continuous, taking these cross products one after another as a series, the series will either diverge or to infinity or come down to zero. And the question was, I asked myself, what needs to be done so that U0 equals UN, A0 equals AN, and R0 equals RN. And this would give me a set of simultaneous equations. These simultaneous equations in a complex space look like this. So I have the velocity vector 1 over a dot and the what's it called, the conjugate of a complex number a star is nothing more than the absolute of the norms squared. So basically, from the earlier, from those three, from these three vector equations, I now define these three vector equations, and this is a Soliton equation. And I will now prove to you that this is a Soliton equation. We start by taking the curl of these two equations that I'll show in blue here. In other words, the curl of A is that and that. We need to evaluate these triple cross product equations, which is a normal thing to do. We know, we already we get because it's a homogeneous and isotropic medium that we're in, the gradient of A and the gradient of R is equal to 0. And so that takes care of those. Now, the one that we need to look at, which I haven't seen used in the literature, is the velocity dot the nabla and nabla dot u. And basically, if we expand it, we can expand it simply as dx, dt, d dx, etc. In other words, these dot products are nothing more than a partial dd dt. And then we've got the other term that we must look at, which are the a dot nabla, which we've not just done here. And that basically evaluates to A, we have to keep the sequence, the partial derivative of 1, because I can put a 1 behind here, is equal 0. And we're left with these two equations. Substituting that in, we get a generic Maxwell equations here with equation 3. So basically, the equation set 2 here and equation set 3 here are generic Maxwell equations taken straight from the mathematics. Page down. Now, we all know that these equations, by doing a further curl operation on the whole lot, leads to the wave equations. And therefore, I've given you the proof that these three simultaneous vector equations give you a generic Maxwell equations, which lead to the wave equations. Therefore, this is a wave equation. I call it the Soliton equation. And basically, if we put in the electric and the magnetic fields, we're looking at these equations define one plane of a moving plane electromagnetic wave. But this is, for me, is very uninteresting. We know exactly these moving plane waves have been studied by many, and I don't want to go into that. But I just basically, it just shows you what can be done. Now, the thought experiment that I showed you in the beginning of the slide, I said I want to separate the electrostatic charge E and the electromotive charge. I also have to give it an E. You know, this is becoming very confusing, and I use the standard E for the electrostatic charge that we find around the electron, and I use this curly E or in script font as the electromotive charge, which would define electric current and the charges on the capacitor. Now, having done that means that I also have to differentiate between the magnetic flux phi, which is normally shown in the slanted phi, and to be different, I have used upright phi for the electromagnetic momentum. Why it's a momentum will become clear in a moment. Now, I define theorem 2, which is the elementary electromagnetic soliton theory. And I shall read it. There exists an elementary length denoted as LO. I always use sub O's instead of sub zeros for elementary. And the elementary time denoted as T sub O, defining the speed of light C such that LO equals CTO. Additionally, an elementary magnetic flux, I call them M flux, phi O represents a quantum of magnetic momentum. Furthermore, an elementary electromagnetic solon, defined by these equations we just studied earlier, carries an elementary electromotive charge to E and has an action H while it propagates at the speed of light. And here, epsilon O is the electric electromotive flux. This is a term that is new to physics, and nobody talks of electromotive or of electrostatic flux or electric flux. Now, the proof that I'm going to will be structured around that I will now derive epsilon 0 and nu 0 without knowing a bit of electromagnetics. We used these two equations earlier because in defining and showing that these are the Maxwell equations. That leaves us this equation, and I say if that is basically defines the motion, and I said it has an action H. Therefore, I multiply both sides of the equation by H. The absolute U is basically a C. Rearrange the terms, and I get H over C phi O squared. These two I don't want to touch at the moment. And the square bracket that I use here is an indication I'm developing a constant. So now I define a elementary electromagnetic action, H sub E, which equals rho H, where rho is simply 1 coulomb per kilogram. Theorem 2 demands that E is transported at a velocity c. Action is momentum times distance. We consider the elementary distance L(O). Therefore, I now write the elementary electromagnetic action as kappa, which is a dimensionless constant, just to get scaling right, because I don't know what the scaling is. And my electromotive charge times velocity times the distance, that is a momentum times the distance, gives me h e. Also, oops, sorry, I was getting phi 0, I said, is electromagnetic momentum. So I already got the momentum. I just need to multiply it by L0 and introduce another constant or physical quantity to do the necessary conversions to get the electromagnetic momentum. That phi e, and then combining this equation with that equation gives me that the absolute of the electromagnetic momentum is kappa e c divided by chi, where chi is a physical quantity with units and scaling that need to be determined. Now, putting that all back into this equation, let's just go back so that into this equation here, equation 5. I put in these terms, and I basically, in yellow, I highlighted the terms that will define the magnetic momentum as h kappa over E, which is the correct way that the same as basically the electric flux is defined similarly as H over 2E. But that can only be true if the rest here that is not highlighted is equal to 1. So now I do all the substitutions. That basically means that 1 over chi equals that. And I get these two terms, which are epsilon 0 and mu 0, which I show on the next page. So I define it as kappa squared over E squared over HC, my epsilon O and mu O, and mapping the normal charge E to E and kappa to the minus 2 equals 2 alpha, I get the expressions that we learn in physics, or what epsilon 0 and mu 0 are. The reason why these two are different is because epsilon 0 and mu 0 are atomic quantities. They are electrostatic quantities that are derived from atomic interactions, and my epsilon O and mu O are basically electromotive quantities. Now we can do some calculations. I can define kappa now as 8.277, which I named the Heaviside constant. Heaviside made all this calculation possible. He gave us the vector algebra. The elementary length is 1.666 times 10 to the minus 24. The elementary time is 5.59 times 10 to the minus 33 seconds. And this gives us a mass gap of 3.683 times 10 to the minus 66. Now, the mass gap basically, I'm going to claim with the Millennium Prize, because one of the Millennium Prizes is to discuss on the Mills-Young and the mass gap. And here I've calculated the mass gap. So as I said, I'm aiming high. Now, we need to find the solutions of these equations. And I need to define some mathematics that I haven't to make things easier. And which is the, with this little diamond here, is a row product. So simply, mathematics doesn't give me a formal definition for if I want to take a common factor out of a row, so that PA11 plus in the matrix PA11, PA12, I can express in this form here. I now define a soliton in terms of velocity, in terms of magnetic momentum, and in terms of electromotive force. I have the quantifier C phi 0 and C phi 0, and A11, A12, A13, X, Y, Z are basically unit matrices, because this column vector here and this column vector here is, I don't need to repeat it every time. I simplify and say my soliton is parameterized by this matrix product. So this is the technology, not technology, the terminology that I carry forward with. All solitons of interest are described by these following three equations. If you look very carefully, you will find all the quantum numbers in here for spin, forward and backwards, but it's all described in the paper. I say N and M, which are in here, are rational numbers. You will see later that I actually need to divide by them and not multiply them when working with solitons. Now, another thing of importance is we must remember that if I have a magnetic momentum flux, which defines a south pole and a north pole, and it rotates around something, if it basically rotated 180 degrees, it is still sourcing a north pole. Now, I need the bar phi is basically I turn the north and the south around. So now I'm sinking the north pole. And then minus phi looks like this. So this is just, we must be careful that we must think here in terms of rotations and not in terms of algebras. When I do 180 degrees rotation, that I've got a negative quantity which cancels out. They don't cancel out. It is, they're always rotations. Now, the most simplest solutions are what I call M-trons here. And there are basically 4 M-trons. You can see with the unit matrix that the diagonal, if it goes in the opposite direction with the a negative, in other words, instead of this would source a north pole, this would source a south pole or sink a north pole. Basically, and if we look at the electric vector, they're both positive. And then, so this is the anti, but I also need what I call the contra with a little dot underneath it. And the difference here is if we do the addition across here, you see there's C, 1 minus 1 is 0, 1 minus 1 is 0, 1 plus 1 is 2. And basically doing the same here, I have minus 2 here in the electric terms. But to summarize it, with all the sum of all of these 4 I call them emtrons because I think of them as particles. The sum of all of them have got an energy component of 4. They have no mechanical recoil, and they have no electrical or magnetic recoil. If I do a M0 plus its anti, I've got a electrical recoil. If I do a M0 plus the contra anti, I have a magnetic recoil. And if I head across that way, so the M0 plus its contra, I have a mechanical recoil, and the basically and the other one here. Now I can now define something moving in a circle. If C equals cos omega 0 t sine omega t, I have something moving at the speed of light going around in a circle. The magnetic vector looks like this, and and if I do the cross product, it comes to 1. Or I can basically have the same with a this one gives me a magnetic, a steady magnetic dipole, and this one, sorry, electric dipole, and this one gives me a static dipole. This here would nicely demonstrate or be used or explain what happens while charging a capacitor. Now I have the photon, which is also what I call a voltron, because this would also be my electric current. Instead of, I purposely put the magnetic vector out on the end. It makes no difference to the cross products. Cross products don't tell me that the vectors have to originate at the same point. They can be anywhere, they are position independent as such. And basically this would be either a circular polarized photon or or an electric current. So if we load this up, we have lots of these being in a circle will give us the magnetic field around the electric current. What I'm not going to go in here today, which I'll do in another talk, where I'll show that I can take this from this diagram. I can derive E equals HF, the Planck's energy equivalence. It's in the paper, which you can download from our website. Another solution, also with the C going in the circle, but now instead of being, I spin up the magnetic and the electric component. This, if we have to take, assume this, so this would be a particle, a soliton. It is also, if I cut this somewhere and make this into a spiral, that would look like the electric currents flowing in the spiral, giving me the windings of a transformer winding. Because I said this can either be a photon or it can be the charge of the electric current. Now, going 3-dimensional, I can now do define 3-dimensional paths, which would look like this. A bit difficult to plot them as I had earlier. When I saw this, these are basically the shells in terms of electrons and shells in terms of nucleon packing. And this, it was 2 weeks ago only that I realized I can build a onion shell model of atomic nuclei using these shells. This is what we're going to continue with now. Okay, let's skip this slide here. Okay, I didn't put, where is it gone? Have I missed the slide? Okay, the nuclear model, and it's basically, I found that to model atomic nuclei, I need 8 shells. Each shell has subshells S, P, D, F, G. And the subshell capacities, this is wrong here. No, it's correct. 1, 3, 5, 7, and 11. I pack them with half charges. So instead of full charges. So a proton would be 3 positive half charges and a negative half charge, which gives me 1. So it's very much different to the quark theory of a proton. After I filled all the shells 1 to 5, I either have iron 5726 or cobalt 5727. The 6th shell onwards, I now need to define in full or add full charges, or but using in my terminology, instead of 4 half charges, we group in 8 half charges. And the 7th shell, which takes me to the end of the periodic table, you will need to group with 16 half charges. And by doing so, explains why iron and actually cobalt, not cobalt, one of the nickel isotopes is the most densest isotopes. Basically, with the half charges, we must always, the S shell also can only accept in terms of 4, otherwise we would only have odd charged atoms above iron, which we certainly not have. Now, it is now very easy. This I'm looking for going forward. I identified if the hydrogen I would show as basically my terminology for an element is a charge at the bottom, its atomic mass at the top. And I show the shells as a 1s shell, 3 positive charges at the top, 1 negative charge at the bottom. So 3 plus 1 gives me atomic weight of 1, and 3 plus 1 divided by 4 gives me the atomic weight of 1, and 3 minus 1 divided by 2 gives me the charge. So now I can start packing the shells. Let's go back to what I call the pitron, which I'll show the symbol pi. This basically is 2 positive charges and 2 negative charges. This would decay into an electron and a positron and 2 pi neutrinos. We will discuss this a lot later. So now it's a simple matter of just adding these shells. As you can see, if we take the helium, the 4-2, and if I need a 5-2 in the P subshell, we are at 5-3 here. I have 7-5. 7 plus 5 is 12 divided by 4 gives me a mass of 3. And 7 minus 5 is 2 divided by 2 retains the 1 charge. Therefore, the isotope, this would define the isotope of the helium-5 isotope. Here's basically we can carry on with lithium. Then what you want to do is from beryllium here. This beginning is a bit messy, but now it becomes quite simple. Now I can use a helium-5 isotope and continue just with a third shell. And boron, I come to carbon, and here are the 3 isotopes of carbon. The 12-6 is and then basically same principle of bumping up. Let me see where it is. 12. I've got a mistake in here, guys. Sorry about this. I will. Okay, no, I haven't. Okay, I have. That should be that 7.5 is incorrect. 7.5 and that should be a 9.7 here for carbon 13 and carbon 14. Then basically, I now. But for nitrogen, there are 2 isotopes. The one uses the carbon 13 isotope. The other one uses a carbon 14 isotope to give me the 2 isotopes of nitrogen. The same happens with oxygen. And then it gets nice and clean. I've always got carbon 14 in as the first place. And then I keep on adding increasing the shell. So here we're at neon, etc. Till we get to the iron. I have the iron, I've skipped a lot there. You can look at it in the table that I have in my paper. It's in the appendix. I have so 57 cobalt. Why I have cobalt 57 in here is because that is carried forward in all subsequent elements and their isotopes going on forward. Now, nickel 6028 is the most what would it be, the highest binding energy. And it doesn't surprise me, to get a 6028, I must have in the proton, I have 1 shell that is negatively charged so that I can get to the 6028. So it's 57 plus 1 is 58, plus the 2 gives me the 60, and the 27 minus 1 is 26, plus 2 gives me the 28, and so forth. We get to zirconium here. I think this is the end where I've gone here. Now I want to show you another video. This will take about 10 minutes. So let me just hopefully get it here. Yeah, let me just move this in properly.
That's what we were predicting. Now, the people that are working on this would be guys like Dr. Lowell Morgan, Tommy Mello, who actually develops the coding for what's called computational fluid dynamics. This is really high-end stuff. It's stuff that's used to do analysis on, like, say, rocket engines and jet engines and so many other things. And we're very good at what we do. This is how we kind of make our living. However, you're going to find out that our predictions were wrong. So we did another model, which you're going to look at here. Right in this area here. This is our analysis of putting in one of our probes. and see what the kind of thermal response that we get. And what the model is telling us is that the temperatures of the gas just off and around the surface of the anode should be around 23 to 2500 degrees Celsius, well within the constraints, or you might say the operating limits of tungsten, which is what the tips are made out of, Langmuir probe tips. But what really happened, I'll show you here. What you're looking at here is the probe tip, and we're going to play this video, and this is a very low powered plasma. So, this is where you say, now you see it, and now you don't. Langmuir probes are about $8,000 a pop, and I had to make a telephone call because we pulled it out. Before I get into that, I just want to let you know the actual power at that time was 182 watts. That's a 182 watt light bulb, imagine, okay? And we're going like, what is going on? So when we opened up Sapphire, we discovered what was left. And this is what the tip looked like after it vaporized with, this is just the residual tungsten you see here on that kind of nodule. That's what was left of it, and everyone knows anything about tungsten, it takes about 6,600 degrees Celsius to boil it. To vaporize it, you need more energy, and in thermodynamics, as some of you probably already know, there's a time domain associated with it and how much heat is lost in the system as well. So it's not just 6,600 degrees. If you're going to vaporize it that quick, it would typically point to temperatures that are much higher than that. And not the 2,300 degrees we predicted, because, you know, the tungsten should have heated up, might have started glowing a little bit, but it should have lived in there. Well, obviously, it didn't. And this is what a tip looks like on the top, before and after. Now, the white stuff is alumina, and its melting temperature is about 3,600 degrees Celsius. So I made a call. Actually, I should back up a little bit here because I got a story to tell you. I called a company who are a great company. You know, I'm not going to mention who it is. We had gone into great detail with them as to what kind of plasmas we're going to get, and they said, we have the probe for you. And so we bought 2 of the probes, and we put the one in, and we talked to him. He said, well, this is what happened. We showed him what was left of the probe tip, and he came back and he said, your plasma's too hot. I said, really? You think? You guys, I said, I told us you guys knew and understood the plasma we have, and we went over this with you guys in detail. And I'm thinking, what am I going to tell Scott? Okay. Then these guys say, let me know when you'd like to buy a new one. So I called Scott and I told him we just vaporized the Langmuir probe, and we did it with only 182 watts, and we don't understand what's going on in Sapphire. It shouldn't have done this. And Scott says, wow, you know what that means? I'm thinking, I just lost my job. Yeah, it means that our thermodynamic modeling is wrong. I'm thinking I'm out of a job. And he says, well, yes, well, maybe. But what's amazing is it means that you have a lot of energy impinging on the probe tip. You might have an effective way of boiling water. And then he says, in his deep voice, do it again. I'm thinking, so we're all gone nuts. The guy just said, my plasma's too hot. The boss is saying, do it again. And I'm thinking, I'm going to have to spend another $8,000 on probes. These things, like 8,000, I said $8,000 a pop, we got to get control over this thing. Because otherwise, you know, we're going to burn through money pretty quick. So we decided to make a new one. Bigger, stronger. I'll put higher pressure nitrogen into the core and cool the core and make it all out of a ceramic to withstand the temperatures. It's going to work. So that's it. That's the new and improved Langmuir probe, much bigger, thicker tip. We figured that, okay, since the plasma is so intense, we don't have to worry about the small wire. We'll put something in thicker and see if we can get some measurements. And what really happened? Again, So I'm going to play a video here, and this is where we got some serious questions and Lowell got involved. But just watch what happens here. This is a macro lens. Everything looks wonderful and good. We're happy.
Adios.
Ouch. Yeah, that's what we said. Well, it lived so far. That's good. Let's just keep it going. Let's see if we can... the motion that you see in a probe is from the forces that are in the plasma. And then it really did some amazing stuff. So we were happy. It actually survived. But the thermonic emissions, as we're going to get into, that's what you call thermonic emissions. That's not, you might say, the plasma. The plasma's gone out by now. So this is just a radiation. This is like when you light up a tungsten light bulb, this is what you get. So the radiation here just grows immensely. We don't know right now why the color changes. We know that we're getting other emissions in here, probably from the tungsten. And this is happening in like nanoseconds. So we go from this beautiful violet color to these colors. We don't know what this stuff is that's flying around in there. We think it could be copper and or iron or whatever. We were able to capture some of these images. But we would have to say that the atmosphere in sapphire is somewhat hostile. And what was interesting is the crater on the side of the anode. So we decided, well, you know what, let's take a closer look at this thing, because we were still getting information back from the tip, which is good news. And so this is what tungsten looks like after it's been machined with diamonds. Okay, it has a kind of a sintered look to it, powdery look. And this is what the tip looked like after we pulled it out of the chamber. So we've seen some cracking with the alumina a little bit. We weren't too concerned. The bright blue color was kind of interesting. But we looked at a closer look at the tip, and we see the grinding marks from the diamond wheel. We didn't see any physical deterioration of the tip, and that was just great news for us. And we thought, okay, we've got something that looks like it's going to survive. And we took a look at the alumina, and it looks like it was starting to melt, so we knew that the temperature was around 3,600 degrees, maybe a little hotter, but still in good shape. And then what I did is I just took my pliers, and we changed the probe up. We just retained it, put my pliers in to pull it out, and it crumbled. And if you know anything about tungsten, it doesn't normally just crumble. And I thought, well, we've got a bit of a problem here. So I put it under the microscope and I looked at it and I said, gee, that doesn't look like tungsten. Comparatively to the two, there's been a huge change in its structure, but not on the outside. The surface on the outside just looked like it was when we put it in. So we started taking a closer look at this, and it was like, what is all this white stuff? And you can see the fracture in the tungsten is very sharp, it's very clean. It's not like we bent it or anything, it just broke. So we decided, and this is when Paul got involved, he says, listen, I know some guys on the University of Toronto, let's get this thing in and get some scanning electron microscopy done. So we did. And I'm going over the material in the tungsten. If you know anything about materials, what you're looking at here, well, the black stuff could be contamination, but the kind of geometrical shapes that you see there above that other stuff that looks like shale is tungsten. It looks like it was getting melted. That shale isn't how it normally looks, but this is on the inside of the tip. On the outside of the tip, it wasn't being affected at all. Not at all. When we did the scanning, when we did the SEM, it was coming back that it was tungsten. The molecular structure, the crystalline structure looked just like it should. We looked inside and this is what we found, and we found a lot more. So we took a look at the anode.
Okay, let me go back to the slides. What happened there? And I believe there was a nuclear transmutation that released a lot of energy in there. And this nuclear transmutation I can explain using basically zinc. I've actually done it for the tungsten as well, but I happen to have the zinc here. If we take a zinc 66 and a zinc 67 and a 68 isotopes, and we look at the 6s orbit, zinc needs an antiproton there to get the correct charge working. And then the 65, basically we add a neutral, it's from 1,3, it changes to a 3,5. So basically I've added a 2,2 to it, and this is what I call the pitron. Now, if I make the calculation, 2 times 60, 2 times of the 67 isotopes getting changed into a 6630 and a 6830. In other words, one moves down and the other one moves up. 3.15 mega electron volts get released. That is about 11.8% of the hydrogen reaction. In the tungsten, it would be 1.44 mega electron volts. So there is a huge possibility that has not been explored of generating clean electricity by the transmutation of the isotopes within an element by electrical excitation, as we've just seen in the video that has happened there. This is my explanation to that video, and with this I would like to end today's talk. The full paper, you can basically, there's a very short link, hmp.onl-182, or you go to the website neophysics.org, and you'll find it right on the top of all the papers that I have in there. Okay, any questions at this stage? Let me stop this here. Okay.
Can I have one question? Thank you for a nice presentation.
Thank you, Christoph.
I would like to ask, in terms of Maxwell equations, if you can summarize, because I was a little bit late on your presentation. Yeah. So what modifications do you introduce, if you can summarize?
What I'm introducing is that basically the Maxwell equations use an electrostatic charge. In other words, and also our physics, the electric current is defined by moving electrons, by electron drift. And the electromotive force is not being used. So, and if we look at Faraday's law, Faraday said the electromotive force is d phi dt, if I'm not mistaken, if I remember it offhand. But the Maxwell equations only apply, in my opinion, only use electrostatic charge. And basically, the current paradigm says that the electromotive charge and the electrostatic charge are one and the same. Therefore, I'm separating the electromotive charge as a separate phenomenon within the electromagnetic phenomenon. So the electromagnetic phenomenon consists of the electrostatic phenomenon plus the electromotive phenomenon. If you take my, in the paper, I actually also, let's go to that slide, which I actually went over. So it was, basically, what have I done? You know, with two theorems, I define a framework to define electromagnetic solitons. But we are required to separate the electrostatic and the electromotive fields or charges or whatever the terminology is extremely difficult to use in this because I'm trying, it'd be extremely confusing to somebody, to talk about it. And I was plenty confused with it. So, I know the difficulties of it. Then I have my solutions of my solitons. And from there, I don't show it here, I can derive the Planck's energy equivalence equals HF, and I can get the origin of mass as an electromagnetic phenomenon and derive the equation equals mc squared from the energies that are defined in these solitons. But I need a complex space to do this. And I unify the forces. I basically, the gravitational and the electrical are both phenomena of the electromagnetics. I have full explanation for all the quantum phenomena. And now you see in the end here that I actually am the first person who has successfully made a algorithmic or written down the laws how to pack the nucleus of an atom in terms of onion shells. So, this gives me so much confidence that I am correct in this. I'm actually, the paper, it's been submitted to the Royal Society. So let's see what happens there. I wrote them a very nice cover letter. Anyway, let's see what happens, because if this would be a complete change of paradigm within physics. I'm basically what I'm saying. I don't know if Maxwell separated, had the electromotive and the electrostatic charges separated or not. But certainly the Heaviside interpretation that we are using for for the Maxwell equations doesn't do the separation. And apparently Maxwell had 13 equations which were reduced to 4. So what was lost? That I've got his treatise, I've downloaded it. You can get it on the archive.org, where the Wayback Machine is also on. And I must really try and read it and study it to see if he separated this or not. Sorry, I didn't share my screen there. My apologies. Let me just share my screen so that you can read quickly what I've done there. Okay, there's this basically what I just talked about. Anyway, while you go through this, are there other questions? Well, I'll leave this up for a while and then come back in person.
You can, I see.
Pardon?
Yeah. So you can always say that's a kind of different phenomenological view on certain phenomena, but of course you try to be as fundamental as possible, and probably you get. I mean, electromagnetism was studied so deeply for last 200 years that it's very hard to question any of the bases. So I assume that most likely the Royal Society wouldn't, or it's hard to say, but politically saying, they are in very difficult position to favor your paper, in a sense of because this paper has to be analyzed extremely deeply if it's so potentially controversial. So
it is extremely controversial. I'll give you 100% correct there. You know, I'll read you my cover letter that I've written to the Royal Society. You know, okay, this is a cover. I'll read it to you. You know that. Thank you for considering my paper entitled "A Novel Constructive Electromagnetic Quantum Theory Describes the Origin of Mass and Unifies the Forces." This paper raises the following dilemma for you. Either the current paradigm prevails, or accepting the mathematical evidence that would overturn it. But as a consequence upon new advances in physical science, it is precisely for this reason that I'm submitting to the Royal Society, who are bound by the Royal Charter and historically were not afraid to support new directions and in thinking from whomever. You know, and then I carry on, you know, with the normal summary, etc. You know, so you know, I'm putting the bull into the china shop there and see what happens.
Yeah,
And,
I see, but
you know, and if you were late to it, I should let's just go back to. Let me just go back into share screen. Share. Did you see that you didn't?
yes, I do see you, right?
You know,
Yeah, I can see.
now we basically, you know, this also took me ages to find this this configuration to work. Basically, from A to B, the electron accelerates. This battery discharges. Between B and C, nothing happens. C to D, the battery deaccelerates, and that battery charges. Now, and the question is, if I keep this electron beam going forever, I cannot explain I1 and I2 as a flow of electrons, you know, and the Drude theory with the quantum modification from, I think, Sommerfeld did the quantum adaptation is the model for electric current. And this thought experiment there shows that it cannot be true, you know, and basically it is thought experiments like this, and it could easily be replicated. You know, I'm going to send it to CERN. They should replicate this, and you know, there cannot be an answer. If you don't want to believe this, then my answer to you is simply, you put in a beam dump at this point here and harvest the energy that you had got for free. Impossible, you know, you know, so anybody who wants to contradict what's saying on the slide, I say, if you contradict this, run to the patent office, because now you can generate energy from nothing, because if there's no current flowing between to accelerate this electron, then you can basically harvest a higher energy content here than here, and that is free energy. It doesn't happen.